হ্যালো স্যার।
হ্যাঁ, কে?
স্যার দীপ।
বলো।
স্যার বলছিলাম যে ওই আমার আর কি অ্যান্সার শিটটা একটু হেজি এসছে ছবিটা, তো আপনার ওটা যদি দেখতে অসুবিধা হয় আমাকে বলবেন, আমি স্যার ক্লিয়ারলি ছবি তুলে পাঠিয়ে দেবো।
না, এখন তো আর হবে না। যা হয়েছে ওইটাই।
হ্যাঁ স্যার, ওটা হেজি হয়ে গেছে।
ঠিক আছে, যা হয়েছে হয়েছে। নেক্সট টাইম ঠিক করে পাঠাবে, কারণ তোমার একবার সাবমিশন করার পর পরে তো আর সাবস্ক্রিপ্ট চাওয়া যায় না।
হ্যাঁ স্যার
ফার্স্ট
মানে।
টাইম যখন করবে, তুমি যা লিখেছো ওতেই আমি দেখেছি, কিন্তু নেক্সট
হুম।
টাইম যখন করবে এগুলো ঠিক করে করবে।
ওকে স্যার।
মানে তুমি এমন নয় যে তুমি সাবমিট করে দিলে তারপর পরে আবার চেয়ে পাঠালাম।
হ্যাঁ।
ফার্স্টেই তোমাকে কেয়ারফুল হতে হবে। ঠিক
ওকে
আছে?
স্যার। ওকে স্যার।
এবং সেখানে চেক করে নিতে হবে বিফোর ইউ লিভ দ্য ক্লাসরুম। ওটাকে চেক করে নিতে হবে সব ঠিকঠাক হলো কি। তা না
ওকে
হলে
স্যার।
পরে যদি বলো আমার এটা হয়নি ওটা হয়নি, তখন তো কিছু করার থাকবে না, কারণ এটা তো পরীক্ষা না, এটা তো পরে করা যায়। ক্লাস হলো, তুমি পরে ডিসকাস করলে ঠিক আছে। এটা সবাইকে কেয়ারফুল হতো। আমি মঙ্গলবার তোমাদের সঙ্গে এ ব্যাপারে ডিটেলস কথা বলবো, কারো যদি কিছু অসুবিধা থাকে।
ওকে স্যার।
গুড মর্নিং এভরিওয়ান।
Good morning, sir.
Just wait, little problem with the system. T03 T06 T07. Can you hear me?
Yes, sir.
Please
Yes, sir.
even Nisa.
Okay. 308
Present, sir.
309,
Present, sir.
310, 310, 311, 313, 316, 319, 321, 322, 325,
প্রেজেন্ট স্যার।
স্যার 3 to 4 আছি।
বলছো না কেন? 324, ওকে,
ইয়েস স্যার।
ঠিক আছে। 401, 406,
Present, sir.
408,
প্রেজেন্ট স্যার।
স্যার 401 আছি।
বলতে হবে তো, কি এখন বললে হবে না,
সরি।
তখন ডাকছি তখন রেসপন্ড করবো। 408,
প্রেজেন্ট স্যার।
411,
প্রেজেন্ট স্যার।
416, still absent, অনির্বাণ নস্কর। 418,
Present, sir.
419,
Yes, sir.
420,
Present, sir.
425,
প্রেজেন্ট স্যার।
427, 428, 429, 430,
Present, sir.
431,
Present, sir.
432,
প্রেজেন্ট স্যার।
433,
Present, sir.
435, 436, 437, 438. Okay, anyone join late?
স্যার 3 to 5 দিয়েছে।
হ্যাঁ, কি বলো?
স্যার 3 to 5 দিয়েছেন।
3 to 5,
Sir, 310.
না 3 to 5 তো ছিলে আগে।
না স্যার আসলে 3 to 4 জিজ্ঞেস করেছিলেন তো আমার কথাটা তখন মানে আসতে হয়ে গেছে।
হ্যাঁ, সেটা আমি শুনেছি, তোমার কথা আমি শুনেছি। নেক্সট কে জয়েন করেছো পরে?
310.
310, 310, ঠিক আছে, আমি দেখেছি তোমাকে।
স্যার 322।
322, anyone else? No, okay. So, do you have any question? What we discussed last time?
Sir, 428.
বলছো
428 attendance.
attendance?
হ্যাঁ স্যার।
No, I am asking whether you have any question on what we have discussed in the last class or even earlier. Nay. Okay. Good. Those who joined late, I'll give the attendance at the end. Not now. Let me go to the class now. Can you see the screen? I hope you can see the screen.
Yes, sir. Yes, sir.
So last time we were discussing actually transients. Last time we discussed the RL series RL circuits. Now today we start with series RC circuit. So let us draw the circuit first. And we have seen in the last class also we discussed that how we can solve or analyze the circuit using Laplace transform. We also mentioned that how we can draw the plots qualitatively from the knowledge of the behavior or property of the circuit elements. So what I'll do today, before doing the analysis, we'll see how the current and different voltages look like as a function of time through plots. So we'll do some plots now without doing any analysis. So again, we have to use the property of the circuits. Here, resistor is, we know that property, capacitor property we also know. But regarding the switching, here the switch is taken from A to B at t is equal to 0. This is the statement similar to that. It was in position, it was open for a long time. I have not mentioned here long time. So we assume that it was open for a long time, or the similar thing, the circuit was in the steady state before it is closed, and the switch is closed at t is equal to 0. Closed means it was taken to position B. Actually, sorry, I should not say it like this. The switch is a different type. So let me taken to B only. Is taken to B. It's taken to B or closed at t is equal to 0. So what will be the current? What will be the voltage across resistors and across the capacitor? Now we will apply the property of capacitor. The capacitor, we know that if it is when you switch on, as I told you, when you switch on, there is a abrupt change. That means in terms of frequency, it behaves as high frequency, infinite frequency. And when the frequency is very high, the impedance of C is 0, is 1 by omega C. So it will behave like a short circuit. So at the instant of switching, it will behave like a short circuit. That means as if it was shorted. So when we switch on, the current that will flow here through this is V by R at the switching instant. So let me have a look at this. So if we wish to plot IT as a function of time, then before switch is closed, that is before t is equal to 0, there was no current because it was open circuit. Steady state means it was open circuit. So let me draw it like this. So it was 0. Now at t, when it is switch is closed, it behaves like a short circuit. So the current that will flow through this circuit will be V by R because it is short. So it will start from this current. So this is V by R. And then at t tends to infinity, so this is the maximum current that can flow. And when it is, after some time, it gradually goes to the steady state. As t tends to infinity, it will be in the steady state. And when t tends to infinity, that is in the steady state, what happens in this process, that capacitor is being charged when you switch on. And initially it was 0. So when it is, if you keep it for a long time, the capacitor will be fully charged. So the voltage across capacitor will be V. So this end is V, this end is also V, so no current will flow. That means the current will behave like this. So it will go to 0 like this. So from this type of current behavior, we can expect just from the property of the capacitor, the circuit element here. Okay. Next, what will be V? VR has the similar relation. VR is equal to IR, I into IT into R. So R is a constant, simply constant, time independent variation I into T. So it will be similar to this. VR plot, and this voltage, this is VRT plot, and voltage will be V. So you start from V. And as there are R and C, so you can easily say it will decay with time constant RC. So tau is equal to RC. That we will show later also. It will decay with the time constant tau is equal to RC. And what about the voltage behavior across C? So that we can do in 2 ways. So total voltage, when before it was connected, there was no voltage we assumed, it is 0. And when it is connected, the VR is this, and the VC will be V minus VR. So if this is V, so if you subtract, it will start from 0. And when it tends to infinity, that is when it is 0, it will be V. So V is the maximum. So it will grow like this. So the capacitor, voltage across capacitor will be varying like this. It will grow like this. You start from 0, it will grow like this. with a similar time constant tau is equal to RC. So what you see that even without doing analysis, we can draw the plot just from the behavior of capacitor. Here we mention another property of capacitor that we mentioned earlier, or inductor. Here the conservation of charge. Conservation of charge should be followed. That means before switching on, the charge should be equal to the immediate charge immediately after switching on. So that means the charge must be conserved in a capacitor, the capacitor system. So here, what is the capacitor charge here? Charge means Q, and Q is C into V. So from there you can write before charging, before switching on, so VC 0 minus is the voltage across this. And after switching on, the voltage across capacitor will be 0 plus. So as there is only single capacitor, same capacitor C, we can cancel out. So that will imply VC 0 plus will be equal to VC 0 minus. That means voltage across a capacitor cannot change instantaneously. So here the voltage across capacitor cannot change instantaneously. In this type of system, it's a system, capacitor system cannot change. We are talking about only one capacitor. So in that respect, instantaneously. In case of inductor, it was the current through an inductor that cannot change instantaneously. And in case of capacitor, we can see that the voltage across the capacitor cannot change instantaneously. So if we know this property, then we can see from the result if what was VC 0 minus, that means before switching on, what was the voltage across capacitor? It was 0. So immediately after that will also be 0. As here, VC 0 minus is equal to 0. So VC 0 plus must be equal to 0 according to this formula. And more general one is the conservation of charge, that is C into V, the capacitor total charge in the system before switching on is equal to total charge in the system after immediately after switching on. So immediately before, immediately after. I am saying immediately because there may be decay after switching, etc. Some other dissipation may be there. So this is how we can draw the plot. And also here you can see that why it goes to V, because as t tends to infinity, the capacitor will be fully charged. So fully charged means this voltage will be equal to this. That is why it will go to V at this point. So in this way, we can draw the waveforms for current and voltage in the RC circuit just by means of the knowing the property of the circuit elements here, as we showed in case of series RL circuit also earlier. Is there any question or any query that needs clarification? সবাই বুঝতে পারছো না, কিছু বলতে হবে আর?
না স্যার, ঠিক আছে।
Okay. Next, let us verify this result now with the analysis. Now we'll do the analysis. We analyze the circuit. So first, we know that we have assumed that VC0 from the given condition, it was capacitor was initially uncharged. It was given the capacitor was initially uncharged. So it will be 0. This is similar to because as if it is given capacitor is initially uncharged. If the capacitor was charged, then VC is 0 minus would not be 0. It will be some voltage there. So this is the initial condition given. Now we write for t greater than equal to 0. We'll write the equation for t greater than equal to 0. The KVL, this will be what? R into IT plus, what should I write for the voltage across this? This is important. What should be the voltage across this? A capacitor. If we know the current, how can we write the voltage in terms of current across the capacitor? Tell someone. I
1 by
is equal to-
C integration
1 by C
I.
integration IDT.
Okay, I is equal to C dV dt. So we have to find V. That means it will be 1 by C, then
I dt.
I, okay, I dt, and integration from the initial value to that instant. But this is not all. You have to add to that I.
0 plus.
I means here I. Here I and IC same. Actually it is IC, but here I and IC same, so we write I 0 minus. That means in this case, while writing the differential equation, you have to write the initial condition. Sorry, not I, sorry, V. This is voltage. This is not I. This is voltage. VC 0 minus, okay? So initial voltage plus this voltage during this time, acquired during this time, T. And this is equal to V into UT. This is a step input. It is on at T is equal to 0 because the input is like this. This is the input. Dt, V. Before it was 0 and after it was V. So it will be V into UT. So RIT plus 1 by C IT dt plus VC 0 minus is equal to this. So note this. From here we will go to the next page. Okay. So if you have not copied this one, we copy this one. We will go to the next page. Not the whole part. I want only this part. Okay. Sorry.
Yes, sir.
So from here we will write the next one. So if you will write then taking Laplace transform you have to mention while doing the analysis, you have to mention all steps. It is not that you will assume what you have done is have followed this. You have to write the steps yourself of both sides. So it will be R into IS plus 1 by C. And what is that? This is integration. Integration, we know that if we have integration, that according to the property of Laplace transform, it will be what? IS by S. So integration means divide by S, differentiation means multiplied by S. But in case of differentiation, we have to write after that initial condition. But here you don't have to write the initial conditions because initial condition is already existing here. So it will be like this. VC 0 minus, this is like a constant, like a unit step function. So VC 0 minus will be VC 0 plus like this. So you can write VC 0 by S is equal to V by S. So if VC0 minus is not 0, then you can do the analysis as we did earlier. Is equal to V by S minus VC0 minus by S. Sorry, 1 S will be there. Let me check. One by C. No, it's okay. Okay, so you can carry with this one, but let me simplify it as we have already assumed that VC0 minus equal to 0. So IS will be V by S into R plus 1 by SC. That we can simplify. As I told you, this should be written in the form S plus A. So if you write it in this S plus A, so you have to multiply both numerator and denominator by S into, you have to divide, or you can say multiply both numerator and denominator by S by S by R. So if you can V into S by R and S into S plus 1 by RC. So SS will cancel. So it will be V by R 1 by S plus RC, 1 by RC. So now this is a very simple form. Now to find IT taking inverse Laplace transform. We know the Laplace transform pair 1 by S plus A. If 1 by S plus A is the Laplace transform, what will be the time domain version? Tell me, if 1 by S plus A form is there, then what will be the time domain version?
E to the power of
E to the power of minus AT, because we know that E to the power minus AT
yes, sir.
ut, this forms a transform pair 1 by S plus A. So these properties, that is the properties you have to always remember. You have to apply the property. So this is then E to the power minus T by RC, and here V by R ut. Ut to indicate this is valid for t greater than 0. So here we see that V by R is equal to E to the power minus T by tau ut, where tau is the time constant. Tau is the time constant, is equal to RC. So we can similarly define here the time constant. If we, from this, if we want to define time constant, in this case, you can see that IT will start with t is equal to 0, it is V by R. And as t tends to infinity, it will be 0. So it will follow this pattern. You can see, verify, we got the same result here also, that we obtained without doing any calculation. And the time constant is tau is equal to RC. Now, how do you define time constant here? So time constant here, again, from this type of variation of current, we can define the time constant again in a similar fashion as before. The tau, when t is equal to tau, the IT reaches what? That was 63%, so it will be 37%. So 37% of the initial value. This is 37% of the initial value. So this will be tau, 37% of V by R. So when IT reaches 30 drops, when current drops to 37% of its initial value, because here initial value is the maximum. We talk in terms of initial maximum value. If it is decaying, we say initial value. If it is growing up, we say the final value or the max steady state value. And if it is growing, we say it reaches 37%. If it is growing, we say 63%. So remember this. Another point is, if t is equal to 4 tau, at a time t is equal to 4 times the time constant, the current reaches 2% of V by R, initial value. That means almost zero, almost vanished. Or when it is growing, we said it is 98%. Again, third definition, if it would grow, it would decay with the initial rate, then at tau is equal to 1, when tau is equal to 1, it would reach the, if tau is equal to 1, it would reach the steady state value. If it would proceed at the initial rate. Okay. Initial rate. That means in the previous case, if the initial rate of current at, that is at t is equal to 0, if we would proceed with the same rate as the initial rate, then it would reach 0 at a time corresponding to tau is equal to 1. Tau is equal to 1. Okay. So tau is equal to 1, or tau is equal to 1, it would reach tau is equal to 1, you can say V by R by tau. V by R by tau. This is actually the slope. So if you remember the previous case, we showed it here. The slope is V by R by tau. So this is V by R, this is tau, this is the slope. That means at tau is equal to 1, it will reach the steady state value here 0. And the previous case, the steady state value was V by R, it was growing, it would reach V by R. So there are 4 ways of defining the time constant. That's 3 ways. And that depends on whether you are discussing in terms of growing of the growth of current or voltage, or decay of current or voltage. Okay. Similarly, if you define in terms of this VCT, you have to define in terms of the growth. It will be 63%, it will be 98%, it will reach the steady state value at V by R. Okay. Is there any question here? এখানে আর কিছু কারো বলতে হবে প্রশ্ন করে? Okay. So we have studied the RC series, RC series RL. We can actually discuss any type of combination of RC, because the principle or the main technique that you have to follow. Before I go to RLC circuit, let me discuss another response, that is the pulse response. Pulse response of RC circuit. Let us look at the pulse response of RC circuit or RL circuit and do anything. So we have this circuit. This is C, this is R, plus minus VC, T, plus minus VRT, and this VIT is actually a voltage like this, pulse. VIT is equal to V is equal to V. This is V. Is equal to V when time is between this T2, say time period tau, duration, is equal to 0 otherwise. That means it exists only for this value, finite value, non-zero value V, and for other regions it is Z. So this kind of voltage is impressed here. So what will be the current in the circuit, or what will be the voltage across it, what will be the current voltage across C, etc., that we will find. Now I will not mention all the steps here that we have discussed in detail earlier. So I will skip some steps, but while you are doing, you have to write all the steps. Now let us see how to solve this one. Here, pulse voltage, so it is like this. So we can see that the pulse is this. This is the pulse, Vt 0t. So we can write it like this. Let me draw it here, then it will be clear. Say one waveform like this, and we have another waveform like this. This is also V. So you can see, sorry, this should be deleted. So this is one function. You can see if you add this to this, so this is plus V, and here it is 0. So this part will be plus V. Here it is plus V, here it is minus V, so it will be 0. So you can see that you can show the pulse as a combination of two voltage functions. One like this, another like this. But what is this? This is nothing but a step function. Okay, this is nothing but a step function. You can see this is nothing but a step function. So this is V ut. And what about this? This point is actually T, capital T. This is also a step function, but that is delayed step function, delayed by time T. So this is V u T minus T. But here sign is minus. So this is the function this. So what we see that then we can write the input function as the algebraic sum of two input, two unit step function. It is ut minus ut minus t. And once we know in this form, now our task is easier. So if we write the current expression for current, then what should we write? Differential equation. What should we write? RIT plus 1 by C IDT plus VC 0 minus is equal to V ut minus V ut minus t. So this part we have already done. Next part is taking Laplace transform of both sides. So it will be R plus 1 by SC into IS plus VC0 minus by S. Then it will be V by S, and it will be what? We can use the time shifting theorem here, T minus T. That means it will be e to the power minus ST into 1 by s. 1 by s means v by s. So because of this time delay, it is multiplied by e to the power minus st. So now we can proceed. I'm not showing it here. So you can solve it. Solve it. So maybe after this you solve for IT. So that is your homework. You try it. This is just some mathematical steps, but not difficult at all. So what we will get after that calculation, let me write it here. So IT will be of this form: V by R e to the power minus T by RC ut. This is the same that we obtained earlier, just previously. This is the same equation, you see. This is the same equation. This is for V by S. Of course, here we have assumed this as 0 to simplify it. And because of this, you will get what? This will be e to the power minus st multiplied. So if you will get the same result due to V by S, but it will be shifted in time. So it will be minus T minus T by RC. It will be shifted in time. And U T minus T. So that is the result in this case. So this gives us the plot variation for current. And if we want to get the voltage, VIT, so VRT will be R into IT. That will be the same expression, only outside it will be V, because RR will cancel out. So it will show similar behavior like IT. And what will be VCT? VCT, you can subtract the V from this one. V is like this. We can do, we have mentioned, there are several other ways to do the calculations. But here I am showing you that if you subtract it, what will you get? If you subtract it, this is V from t is equal to 0 to t. What is the value of this from t is equal to 0 to t? T is equal to 0 to t. This is absent. This is absent. So you will get 1 minus e to the power minus t by RC into, of course, V is there, into UT. This is the same as this one. Okay, I have not written it here. This is due to the first part, and due to the second part, again, it will be subtracted from, this is subtracted from all values of t, and this will be subtracted from this minus V minus UT. So minus V minus UT minus this. It will be again 1 minus e to the power minus t minus t by RC into U t minus t. So that I have shown from here. You can do the calculation directly also from various other ways that we mentioned earlier. But if you have any confusion, you always tell me, let me know, because of shortage of time I have skipped the details, because I assume that you have understood it. But still, if you have any problem, let me know. I'll explain it again. Is there any problem here? I told you earlier also, how can you find the voltage not only by one means, there are 2-3 means. For example, VC. Here I have found VC just subtracting this, subtracting VR, subtracting VR from VC. So it will be like this. We can do it also like this using this formula, because VCT is given by 1 by C I dt. So you can take the integration and use this limits. Then also you will get the same result. This is the second way. And the third way of finding VCT is you find the VCS. That means that Laplace transform of this. That is IS by 1 by SC. You find VCS, then take the inverse Laplace transform. So at least we can see there are three ways by which we can write the function. And if this function you cannot explain graphically, then you can do it in two ways. One is directly by using this formula, or from Laplace transform version, then doing the inverse Laplace transform. Okay, do I need to clarify anything here for details? If it is not clear, let me know. Don't hesitate. Let me know. I can tell you. I can mention, okay, maybe. So VCT, you can calculate 1 by C 0 minus T IT dt plus VC 0 minus. So this is known. This you have calculated, so you can easily find VCT. That is one way. Second way is you find VCS. VCS is equal to IS by SC plus VC 0 minus by S. So now we'll get an expression. Then inverse Laplace transform. That will give us VCT. So that is the two ways by which you can do this one. And the third one, if you know the plot, or if you know the expression for VCT, so VCT will be equal to V input VIT minus VRT, or VIT and VRT is nothing but here in this case R into IT. So you can find this one. So I have seen, I've written here again. So if it is not clear to you, so you can write in this way. Three ways we can find the VCT. Okay, let me tell you also one more thing. So if you are asked to find only VCT, not IT, then you may skip the steps of finding this and this, because IT is not needed. So why don't you directly calculate VCS and then take the inverse Laplace transform? So that will be a quicker step to find VCS if IT is not needed. Okay. Is there any question here?
Yes, sir.
No? Any question or any query? Similarly for VLT also, for RL circuit also. Any question? Yes or no?
No, sir.
Okay. Now I am going to another important part. Let me go to the next page then. For the same, so our input is this. This is VIT is equal to 0. We have not drawn the plot of that, right? Remember that you have to draw the plot also. In this type of problems, not only the calculations, you have to draw the plot also. Okay, here it is V, input voltage, that is V, and this is time t. Now, VRT. What is VRT? Let me write here. VRT is V e to the power minus T by RC UT. I'm writing what I wrote in the previous page. I'm writing the same thing. It is not new. T minus T by RC into U T minus. Okay, so I want to draw this. How can I draw? So this has two regions. One before T, before T, small t less than capital T, this part is 0. So it will be contribution only from this part. And that is nothing but a decay with time constant tau. Let me assume that it is decaying like this. So this is the first part. So it has reached at a point. What is the value at this point? At t is equal to T, the value of this voltage is e to the power V into e to the power minus T by RC. You can easily see here, put the value of small t is equal to capital T. So the voltage has dropped and reached the value V e to the power minus T by RC at this point. Okay, this is a contribution from here up to this. And after that, what happens? After that comes this additional term. It's minus T by RC. That means it is also decaying term. Decaying from where? From negative value. Starting from negative value. Decaying means it will, as t tends to infinity, it will be 0. So let us focus on this first. So at t is equal to T, what is the value of this? What is the contribution from this part? At t is equal to T. And let me write with a different color for here. Is there any other color? So T, oh, it's not, oh, we cannot see it. Okay, black. So here at T, black is not prominent, it is a pencil. At T is equal to T. When T is equal to T, what is the value of this? The voltage V is multiplied. Remember, it is minus V because this is 1. So at T is equal to T, contribution from this is minus V. And contribution from this is this. So at T is equal to T, the voltage will be this minus V. That means the voltage will go below by an amount V, and it will be here. And after that, then it will decay like this. So this is the plot for this. Okay, let me write here a red version because red is for this plot. So it has reached a value. What is the value here then? So at this point, the value is V e to the power minus T by RC minus 1. So that is, as this is greater than this one, so it will be negative. But after that, again, we see both the cases is showing decaying with RC time constant. So it will decay with RC time constant. As t tends to infinity, both shows that it will be 0. So the plot for this will be like this. This is the plot for, this is the, sorry, this is the plot for what? V, oops. This is the plot for VR. So the input is like this, output is like this. And if I want to draw the voltage, that is VC. So let me write the VCT. What will be VCT? VCT, we wrote it already earlier, the previous page. 1 minus e to the power minus t by RC into UT minus 1 minus e to the power minus t by RC into U t minus t. And this is easy to understand. I am drawing it separately so that, or maybe you can draw it here also. So you see here, it is showing the increase. In this increase, that means it will charge. So what is the voltage at this point? It will charge to that value. So it will charge to such a value that the sum of these two will be 1. So if this is this, so it will go to a value, say somewhere here. Say this point value is, okay, let me change a confusion of color. Let me make it red. Okay, this is red. And for this, I will draw it black. So it will then exponentially, rise to this value. What is this value? This value is V into 1 minus e to the power minus t by RC. We'll go to that value. And what about this here? Here also, you will see, if you do the calculation, if you check it here, you will get the same value here also. And after that, it will decay like this. So this is the plot for VCT. So you can see that if we apply a pulse, how the voltage waveforms look like in this case for VR as well as VC. So now let me draw only the two parts. So this is the pulse input, and it shows variation like this, such that this gap is V, this is for VR. And VRT shows this type of behavior, VCT. So it may so happen that the plot is like this, because where it will reach, that depends on what? which value it will reach, that depends on what? That depends on the value of RC. So if we have RC decreased, if RC decreased, then what will happen? If RC is decreased, this value will be larger or smaller? If RC is decreased, you follow me?
The larger.
If RC is decreased, this value will be larger or smaller?
The larger.
No, not larger, it will be smaller. Because if RC is small, then T by RC is large, and e to the power minus T by RC will be small. Exponential minus large means it is small. Right? If RC is small,
Yes,
T
sir.
by
I have.
RC is large.
I have
So
missed the
exponential
minus.
of minus means it will be small. So if RC is very small, it may so happen that the plot looks like this. It can so happen like this. It can almost, in a very short time, it can reach the zero value. And it goes to zero like this. And from here again, it shows the plot like this. So that will be, that can also be VRT. And in that case, what will be VCT? VCT will reach the maximum here. And it will reach, go down from here. This is from VCT, VRT. This is VCT, and is a zero, so it will be like this. Okay. So this is the plot for, this will be the plot for and this is the plot for VCT. So depending on the value of RC, so here you can say RC large. Here is the case when RC is small. So let us look at the cases one by one. So when, if RC is very small, that means tau, time constant is very small. If RC is very small, so this will even reach closer, very close to zero. It will almost immediately reach zero. And VRT will reach almost immediately zero. And VCT will be nearly equal to V. That means the voltage across the capacitor, so voltage across capacitor reaches, that is VCT. VCT reaches V very quickly. You can see here, if tau is very small, this VCT can reach this stage very quickly. If it is smaller, it will reach here. It will reach VT here. If it is even smaller, it will reach here. So if tau RC is very small, VCT is reaching V very quickly. That means we can say approximately VCT, we can say approximately equal to VT, VIT. So VCT is approximately equal to VIT when tau RC is very, very small. Okay. Then what will be the voltage across capacitor? VRT. VRT we know R into IT. And what is IT? IT means assuming there is no initial voltage across capacitor. So you can write IC R into, sorry, we need to find IT. IT means C D VC dt. If we know the voltage across capacitor, C dV dt will be current, right? And this shows that this is approximately equal to, dVi dt. That means if we take the voltage, and if we take the output voltage across resistor under the condition RC very, very small, then VRT is actually, this is a constant. Apart from this constant multiplier, it is the differentiation of input voltage. So it means that it is acting as, so it acts as a differentiator. So under this condition, the RC circuit will act as a differentiator. Got it? Or I need
Yes,
to
sir.
say it again. So it means that if you have a circuit like this,
Sir, can you please show the previous slide? I am actually copying the equation.
it acts as a differentiator. Or let me put it here, the same. So if we have VIT if we put C here, V here, if we take this as our output, V O T output across R, and here time period is T, and RC, tau is equal to RC, is much, much less than tau, this time period, this time duration, RC tau, much, much less than T. So then it will be act as a, we can show this, we can use this block, if you take the output across this, so this block is nothing but a differentiator. That means mathematical differentiation, this circuit will do the mathematical differentiation of the input voltage. So in this case, okay, let me go to the next page. So if your input is like this is input, VIT, V, this is 0, this is T, this is T. And if you differentiate it, how will it look like? You are given a waveform, you have to differentiate it. How will you do that? In an ideal case, if it is doing abruptly, you will get a pulse here if you differentiate it. And in this region, it will be 0 because this is constant. And in this case, again, it will be pulse in the negative direction. So if it is a practical, it is not infinitely changing, then you will see a pulse like this. And here you will see a pulse like this. So if you differentiate this, you will have a waveform like this. and you can verify it in this case, that VRT, it is showing the differential. This is actually the differentiation of the pulse. If you differentiate this pulse, you will get the waveform like this. In practical case, it will be just a single pulse, impulse one, but practical case, you will have a very, very small duration of this kind of pulse. So this will be the plot. So if we are giving this input and if it is differentiator, the output will be like this. Okay, is it clear?
Yes, sir.
What about others? Only Shayan is saying, but no one else. Okay, so next part, so that is here we have shown a differentiator. So what is so if I ask you when a RC circuit can act as a differentiator, so what would be your answer? Your answer would be if the time constant of the RC circuit is very, very small compared to the minimum time duration present in the waveform. Here it is pulse, and the voltage is taken across the resistor, then it will act as a differentiator. So that will be your answer. That means for condition for RC as well as where are you taking the voltage output. Okay, remember this, just all RC very small is not enough. Small with respect to what? For example, you can have a pulse like this. You can have a pulse train like this. So it will be differentiator. You have to check the smallest duration. See, your RC should be very, very small compared to the smallest duration of any time varying components, pulse components, or time variation components in the input waveform. Here I have shown only one, but there can be many such. So to ensure that RC is very, very small compared to this T minimum time period, or minimum time duration of pulse in the input. That is one condition. And next condition, you have to take the output across. Output should be taken across R. Then only it will act as a differentiator. So let us see the other case when RC is very large. When RC very large means much, much larger than T. So in this case, it will be much, much larger than if you have several components. If this is T max, it will be larger than the maximum duration. Okay, so in that case, we go back to the previous slide. You can see this is the case. So if you increase your time duration is large, that means it will remain almost flat. It will decrease very slowly. When RC is large, this is increasing. So if RC is very large, the drop will be very small. It will be almost flat. So it will behave like almost, it will show behavior almost like this. It will be almost like this. This will be your what? This will be VRT. It will be like this, almost same, reached V. And what about VCT? VCT is just a subtraction of this. VCT will increase very slowly, almost in a linear fashion. So this will be VCT. This is VRT. This is VCT. T is equal to T. Okay, so this is our plot expect to see. So in this case, we can write then VRT is approximately equal to VIT. That we can read. VRT is approximating the input voltage because this is our input voltage, VIT. Now, we have to find then VCT, voltage across capacitor. What is the formula for that? 1 by C 0 minus T I dt. And here we assume that initially there was no charge. There was a DC part constant. We are looking at only the changing part. So if that constant part is 0, this will be VCT. Now here we can write 1 by C 0 minus 0 to T. I means VRT by R into dt, and that again VR means R into I, sorry, VR by R, so it will be VR 1 by RC will be go outside, and inside VR is approximately, let me write it here, VRT dt. So we see that VCT is approximately equal to, apart from this multiplier constant, it is the integration of VIT dt, because VRT is nearly equal to VIT. So you can see that then it will act as an integrator. So it acts as an integrator. So under this condition, so under what condition? If RC time constant is very, very large, so large that it is larger, much larger compared to the maximum time duration component present in the waveform, and the voltage is taken across capacitor, then it will act as an integrator. So you can draw the circuit like this. This is R, this is C, this is be our integrator. Here we have input VIT, and the output is here V0T. If you output take across, this is black box, is nothing but an integrator. Okay, now look at this waveform. If we integrate this, what will happen? This is our input VIT. If we pass through an integrator, so this is fed to integrator, so the output will be what? You integrate this. This is the black box, is an integrator. So after the output, that means at this point, what will you get? If you integrate it, just a waveform. If you integrate means is the summation of the area. Integrate express the area. So here area is 0. So as you progress, the area will increase. And at this point, area will be maximum. So it will be like this. It will go increase like this. And this is the same that we obtained here. So integrator means that it will be varying linearly with, almost linearly with time. This is if it is a pulse. From the pulse, you can get a ramp type of input for this duration. So we see that an RC circuit can also act as an integrator if the RC time constant is very large compared to the maximum time duration component present in the waveform, and also the output is taken across the capacitor. Then it will behave like an integrator. Okay. Is there any question here?
No, sir.
Okay. If not, then let me give you a homework to do it. Show when a series RL circuit behaves as an integrator, and second, a differentiator. So this is the task. If you have understood it, you have to do it yourself. Differentiator. So this is your homework. So I'm not discussing. Similarly, we can do this one. Okay. Now we go to our series RL circuit. RLC circuit. RLC plus minus V. Switch is closed at T is equal to 0, and you have to find the current in the circuit. So we have discussed in detail earlier. Also, we assume initial conditions, say I0 minus equal to 0 or Vc 0 minus equal to 0. That means initially in the steady state with no magnetic or electric energy stored. This is the condition. So in this case, you have to find RT. So what should we write? We write the differential equation. Now I am skipping the steps just to make it, do it quickly. L di dt plus, what should I write here? 1 by C I dt plus Vc 0 minus is equal to the unit step, so V ut. And if you take the Laplace transform of both sides, it will be R is plus S L is plus 1 by SC is. Here was actually minus IL0, that I have used IL0 equal to 0. Vc0 is also 0. So we write V by S. So from there, we can write IS. We can simplify it after some steps. V by L is equal to A square plus S into R by L plus 1 by LC. So this is just a mathematical simplification. You can write it like this. And it shows that, okay, so as we mentioned previously, I think, so we can write it like this. We write 1 by LC is equal to omega 0 square is equal to 1 by LC. This is the natural resonant frequency of the circuit, 1 by LC, to denote the by omega 0, and R by L, that we write R by L is equal to, or R by 2L is equal to zeta omega 0. So then we can write here A square plus 2 zeta omega 0 plus omega 0 square. So you can see that its current response will determine on the behavior of this part. And this shows that it has two roots. It will have two roots. One is say S1, another S2. And what are the roots? Roots are minus zeta. You can solve this quadratic equation. Put this equal to 0. S square plus 2 zeta omega 0 plus omega 0 square is equal to 0. It will give us two roots, plus minus zeta square minus 1 into omega 0. So that means one root corresponds to plus sign here, another root corresponds to minus sign here. So if we take this value here, then we can write IS after doing the partial fraction, after simplification of this. Okay, let me write it here first. So V by L, this is equal to S plus zeta omega 0 minus zeta square minus 1 into omega 0. We can write it like this. And S plus zeta omega 0 plus root over zeta square minus 1 omega 0. We can write it like this. So S plus A into S plus B. So we can write it in this form: V by L into A by S plus A plus B by S plus B. This A is this, B is this. And you can find A and B by partial fraction technique. So that you can do. I'm not doing that because you know this already. So I'll write the result after doing that. IS will be given by V by two L zeta square minus 1 square root into omega 0 okay, let me tell you. It will be 1 by S minus zeta minus root over zeta square minus 1 omega 0 minus 1 by, you can check all these calculations by yourself also at home. So you will get, after that partial fraction technique, you will get this result. And from there, we can take the inverse Laplace transform to get the result V by 2L zeta square minus 1 omega 0, and this is S plus A, means S plus A means what will be the inverse Laplace transform? We know 1 by S plus A means e to the power minus AT. So it will be e to the power this into T. Okay. No, it is actually plus, sorry. It should be plus. So e to the power minus zeta square minus 1 omega 0 into T. And from here minus eta minus zeta minus plus eta square minus 1 omega 0 into T. I don't need to write it here now. And from here also again you can write 2L eta square minus 1 omega 0. So this is common, e to the power minus zeta. I think I missed one thing. This is actually omega 0 is multiplied to both of them. Omega 0 is multiplied to both of them. Okay, so zeta omega 0 T, this will be common, and here it will have e to the power root over zeta square minus 1 omega 0 T minus e to the power root over zeta square minus 1 omega 0 T. So this will be the response for IT. And we see that consists of exponential functions of different nature. So this part shows the exponential decay like this. So this time will show the exponential decay like this. But this one, we do not know, sorry, this is minus. We do not know how it will look like. That depends on the value of zeta with respect to 1. So here, we discuss different cases. For example, if case 1, zeta is greater than 1. If zeta is greater than 1, then this is positive. This is also positive. So the square root will be real number, and square root is real number, and this is nothing but the hyperbolic function. Okay. So I am not writing this part. This part is I just as it is. Only this part. It will be what? It will be this minus this. This is sine hyperbolic function. Into omega 0 T. This is sine hyperbolic function. And then you have to multiply it with 2 to get this value, this by 2. So it should be multiplied by 2. So 2 will come outside. So its variation will be according to sine hyperbolic function. And if we get a plot of this, if we want to try a plot of this. So in this expression, we have two types of variations. One is exponential decay. Another is this. And the combination of that will give rise to plot of IT like this. It will go reach a maximum and then drop. And under this condition, the circuit is said to be overdamped. The circuit is overdamped. So under overdamped condition is then when it is zeta greater than 1. What is zeta? It is R by 2L into omega 0, that is greater than 1. That means this will happen when the resistive component is very large. So resistive component gives rise to damping. So when resistive component is so large that it is greater than zeta is greater than 1, then we say that the circuit is overdamped and its plot will be like this. Okay. Next we go to another case. Say zeta is equal to 1. If zeta is equal to 1, this shows 1, this shows 1, so this becomes 0. But actually it is not so. When zeta tends to 1, we have to calculate it in the limit. Zeta tends to 1. And if you do that, case 2, zeta is equal to 1. Now calculate it in the limit zeta tends to 1. Because you cannot apply here zeta is equal to 1 directly. If you put zeta is equal to 1, you see here this will be 0 and this will be also 0. This is 0 by 0 form. And you know that 0 by 0 form means you can apply either L'Hospital's theorems or you can that means using the in the limit. So you know the L'Hospital's theorems. So I am not also going to discuss that. But if you do not know, then let me know. If you forgot it, then only I will tell you. Otherwise, I'll assume you know it. So apply the L'Hospital's theorem. L'Hospital's theorem, you take the differentiation of both with respect to zeta and then put zeta is equal to 1. So then you will get Is is equal to V by L into S plus 1 by LC whole square. And this is the case like V by L, this is S plus omega 0 square whole square. So this is the case like where we have the transform like this 1 by S square. So when we get the transformation like this, when do we get transformation like this 1 by S square? Or which type of function? It is T, ramp function. Forgot it. We just did it yesterday.
Yes.
So for T, it is 1 by S square. That means in this function, there will be T involved. Plus S is replaced by S plus omega. That omega 0. That means there will be and 1 by S plus omega 0 says that there must be e to the power minus omega 0 t term. So that shows that if you take the current response, it will be V by L into T into e to the power minus omega 0 t. Of course, ut. We are talking about ut. So this is the case for this case, and this is called critically damped. This is a situation called the circuit is said to be critically damped. And then we can find also R by 2 omega 0 L is equal to 1. So you can replace omega 0 is equal to L by C. Then you can find the relation between R, L and C under this condition from here. Now case 3. Zeta less than 1. So go here. If zeta is less than 1, the term within the square root becomes negative. And if it is negative, then it becomes imaginary. Square root becomes imaginary. And if it is imaginary, then we can use the Euler's theorem to get the sine or cosine function. So in that case, so it will be j, so it will be is will be v by l, sorry, not is, let me write it, it is equal to v by 2l zeta square minus 1 2l omega 0 zeta square minus 1. So that will be j into 1 minus zeta square. And within bracket, we have this one. So 1 minus zeta square, it will be then e to the power j 1 minus zeta square omega 0 t minus e to the power minus j 1 minus zeta square omega 0 t. And by Euler's theorem, you know that we can write it as 2j sine omega t. So then you will write, if you write 2j sine omega t, v by 2j sine omega t, this is actually 2j sine omega means here 1 minus zeta square omega 0 into t. So it will be cancelled, 2j will cancel out. So it will be omega 0 L root over 1 minus zeta square sine omega 1 minus zeta square omega 0 t. This is the case the circuit is said to be underdamped. So if it is underdamped, then what you see that, sorry, one term is missing, e to the power minus zeta omega 0 t. So e to the power minus zeta omega 0 t. So this expression look like it's an amplitude modulation. This is as if the signal, and that is modulated by this variation. This is the envelope. So its plot will be like this. Like this. So it will, this is the exponential decay term. That is envelope. It will follow e to the power minus zeta omega 0 t. And this is due to the second part here. And its time period here, frequency of resonant frequency omega 0 dash will be 1 minus zeta square into omega 0. That means it is less than the natural resonant frequency by this factor. So undamped oscillation, so sine term means, sine or cosine term means there will be oscillation. So the circuit will show some oscillations with gradually decaying amplitude. And this is the nature of undamped response of a circuit. So IT will behave like this. Case 4, I am not discussing details, but case 4 is very simple case. You can calculate IT is equal to what? This is the condition for zeta is equal to 0. If zeta is equal to 0, that means R is equal to 0. That means if there is no resistance in the circuit. If there is no resistance in the circuit, then if you put zeta is equal to 0, this will be 1. You can put here also. Zeta is equal to, this will be 1. This will be sine omega t. So it will be V by omega 0 L sine omega 0 t. That means it will oscillate without any decay of amplitude. So this is called the undamped. This is called the undamped oscillation or undamped oscillatory circuit. So this circuit will behave as an undamped oscillatory circuit. That happens when there is no resistive component in the circuit. So we can see very interesting results from the simple RLC circuit. It can respond differently depending on what? Depending on this particular expression, this particular equation, solution of this equation. That means roots of this equation. And this equation is called the characteristic equation. So it is the characteristic equation of a system that determines the response of the system. So characteristic equation of a system is very, very important to know. So it is a characteristic equation of the system. Here, it is S square. We can write in this form S square plus A1S plus A0 is equal to 0 of this form. And this is called a second order system because the highest power of S is 2. So the second order system, so oscillation we will see at least the system should be a second order system. Then only you will see the oscillation. Anyway, so what we have seen that the behavior of the characteristic equation, the solution of the characteristic equation, that determines the nature of response of the system. And there can be different cases. The system can be the RLC circuit is an example of RLC circuit is an example of second order system. In general, for nth order system, in general for nth order system we can write an s to the power n plus an minus 1 s to the power n minus 1 dot 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 finally a0 equal to 0. This is the nth order system. And nth order system, if the roots, the condition is roots are real. Let me write first. Real, negative, and unequal. If the roots are real, negative, unequal, then the response is said to be overdamped. So in the previous case, you can easily check that in our case, what are the roots? The roots were this, minus zeta omega 0 t and zeta square. Roots were this. This is one root, another root. And zeta square minus is always less than zeta. So the roots are always negative. And zeta is greater than 1, so that is real. So real, negative, and also there is one for plus value, another for minus value. So the roots are real, negative, and unequal. Then the response will be overdamped. But the roots are negative real and equal, whenever it is equal, it will be critically damped. When the roots are real, negative, and equal, it is critically damped. Number 3, third case, if the roots are, instead of being real, if the roots are complex, and if they are complex, they must be in conjugate form. If one root is a plus jb, another root will be a minus jb. The complex conjugate, then it will be with a real part negative, then it will be under damped. The circuit is said to be under damped. You can check the previous case. In this case, this part is real, part is negative, and imaginary part is, this is real part negative root, and this is another part of the root. This is complex conjugate. This is the complex one, is the conjugate of the other one. So it shows the underdamped response. And if real part 0, it is complex conjugate, and real part 0, then it will be undamped oscillatory. If it is real part is greater than 0, positive, we are not discussing any case which is real part is positive, because real part is positive, it will grow, and that will violate the energy conservation law. It cannot happen. It will grow with time. That is why, and that is an unstable system. So we are discussing stable system. So that is why we have not considered any real part 0, because real part is greater than 0, then it will show increasing gradually, and that cannot happen. Okay.
Yes.
There
Sir,
are.
actually, we have another class from 12.
Yes. Bolo.
We have another class from 12.
Shampar class to. SD madam
Yes,
class
sir.
to. She will take class from 12.
Yes, sir. Yes, sir.
She will take class from 12:50.
Okay, sir. Okay, sir.
Okay. Rules is that if the roots are complex, if the roots are complex, they are always in conjugate pairs. That means one root is a plus jb, then there must be another root a minus jb. It is not that only this or only that is present. That is not possible. And if n is odd, if n, the polynomial degree is odd, then at least one root is real. At least one root will be real, and others may be real or imaginary or complex. And if n is even, no roots may be real, there may be no real roots, or real roots are in even numbers. There will be 2, 4, 6 like this. Because the complex conjugates will always appear in pair. And if we have a higher order system, then the response is mainly controlled by usually the first and second order response. So before I close, let me show you how we can know from the plot in the Argand diagram. That is the complex plane. This is the complex plane or S plane. This is j omega and S. So roots of characteristic equation we can plot in this plane, and this is to the right, this is to negative, this is sigma. This is sigma S is equal to sigma plus j omega. So this is plus sigma, this is minus sigma, this is plus j omega, this is minus j omega. And if we have a root here, real imaginary axis, then the response for that, from that we can say what will be the response. If we have a root here, its response will be like this with time, decay. And if this is A, it will decay with e to the power minus at. So from this root we can say, if we have one root here, so this is a complex, so say this is B plus JC, then there must be another one which is B minus JC, or let me say it's not B, minus B, this is on the imaginary side. So in that case, so for this case, the response will be like this. We have a real part, negative, and imaginary conjugate. That means it will be underdamped oscillation. So it will show within this envelope. The envelope is to be governed by e to the power minus bt, and it will oscillate like this, and its omega 0 dashed will be equal to C. So from here we can find this one. This is omega 0t, this is the oscillation frequency. And if we have roots only here, this is JD, and this is a minus JD. Then for this case, you can see there is no real part, so it will show undamped oscillation. It will go like this, and the frequency omega is equal to D. Here, it will give. And if we have a root here, then the response for that, this is the real part positive. That means it will grow exponentially. It will show a plot like this. It will grow like this. Similarly, if we have a plot here, roots here, it will have, so it has real part positive and there is imaginary part. So it will show, this is the envelope, go like this. and the envelope is given by this one. I have not shown it here. This is the envelope. So similarly to this one. So we see that if we know the characteristic equation, roots of the characteristic equation, from there we can know the response of the system. So if we know the characteristic equation of a current in a circuit, then we can find from the roots the nature of response in the circuit. And this should, if you are asked to do so, you can show it like this. And also you can, this plot should be informative, means you have to indicate what should be the value here, V, what should the value of omega 0, etc. Okay, so that's all for today. And we will conclude in the next class, that is on Tuesday. The Tuesday our class was from 10 to 12 or 11 to 1?
Sir, 10 to 12.
Sir, 10 to 12.
10 to 12. Okay, so we'll meet next on Tuesday at 10 to 12. So in the first hour, we will complete our remaining part of discussion. And then next hour, we will discuss other issues. And also, hopefully, I will show your answer script and discuss on that. Okay? Okay, so
Okay, sir.
you...
Okay.
So if possible, on Tuesday, can you shift the timing from 9 to 11 a.m.?
What? You want to do it from 9?
No.
Huh? I do not understand. Why do you want
No,
Huh?
no, actually, that day I have a train from 1 p.m. So,
No. My class will be up to 12.
no, I am saying that from 10 to 12 you have your class. So, can you shift the timing to 9 to 11? That's what I'm saying.
No, that, but you don't have any other class after that, right?
No, we don't have.
No, I don't understand. Why do you need that time? What about others? What do you tell?
So it will be better if you could shift the class from 9 to 11.
9 to 11. You
Yes,
want
sir.
it, all of you want it to from 9 to 11. Okay.
Yes, sir.
Yes, sir.
Okay. Then it will be 9 to 11. Okay.
Okay,
স্যার
sir.
আমার প্রেজেন্টটা দেওয়া হয় না, একটু দিয়ে দেবেন?
Okay. Just wait. কি নাম বলো?
স্যার রাহুল চট্টোপাধ্যায়, রোল নাম্বার 321।
রোল নাম্বার 3 to 1.
স্যার আমারটাও দেওয়া হলো
3 to 1.
হ্যাঁ
হ্যাঁ।
303
আর কে
303 স্যার
303 শ্রীধর
Yes, sir.
শ্রীধর
Yes, sir.
Sir, 429. 429.
429
Yes, sir.
name
Shayan Mondal.
Shayan Mondal. Anyone else?
Sir, 427.
306 Sheikh Mosibul Islam.
Okay, wait. 427 কি নাম?
Yes, sir.
নাম
Shahana Rai.
আর কে বললে?
306 Sheikh Mosibul Islam.
306 anyone else? হয়ে গেছে সবার? Okay, if it is done then you may leave now. Thank you. We'll meet again on Tuesday at 9.
Okay, sir. Thank you, sir.
Okay, sir. Thank you, sir.
Okay. Thank you.